Hey everybody, hope everybody's doing well. And I know it's been a while since I've seen you there at the school, and I know we'd all like to be there, but now we gotta try and do what we can do from home. And so I'm trying something a little bit new. This is the first time I've done one of these. We're gonna go ahead and give it a shot and see how this goes. Hopefully it works for you. You guys will have to let me know. All right, so what we're gonna be talking about today is something called vector fields, and that's really that's a math topic, but it has a lot of application in physics, and we're going to get into how those vector fields relate to physics and specifically gravity. Before we talk about a vector field, I want to remind everybody what a vector is. Remember that a vector is just a measurement that has magnitude and direction. So, like mass, let's say my mass is 70 kilograms. There's no direction to that. But remember, if you're talking about like, okay, you're driving, well, how fast are you driving and which way, right? So something that we didn't talk a whole lot about is that you can represent vectors with an arrow. And so here's a couple examples. So let's say someone's traveling 4 meters per second. They're driving, they're going 4 meters per second east. And so we can represent that with an arrow, and I'll go ahead and draw one here, and it's going to point to the right because east is usually to the right on a map, and let's say that's about 4. Okay, so if this is 4 meters per second east, then let's look at what 8 meters per second east should look like. Well, 8 is double 4, so this arrow should be twice as long, and the direction is still east, so it's still going to point the same way, but they're going twice as fast, so their arrow is twice as long. Roughly, okay, just do the best you can. Now, let's say the last example, 8 meters per second west. So this arrow is 8 and 8. So this arrow should be the same size as the last one, but now it's going west instead of east, so it should point to the left. Kind of like that. So just a really quick reminder, vector is really not that complicated. It just has magnitude and direction. And to show that, we can just draw arrows. The bigger the number is, the bigger the arrow is, and the arrow should, of course, point in whatever direction we need it to. Now, the thing that gets really interesting about these is maybe I didn't want to draw this arrow over here, right? I can draw this arrow wherever I want. Maybe I draw it over here. And that's just okay, right? Because these are approximately the same size anyway, approximately, but they're about the same size. And so those two arrows, and they're about the same size, and they point in the same direction. So these both are 8 meters per second east. I can draw the arrow in whatever spot I want. What's more important is the size of the arrow and which way it's pointing, not really where it is, right? That's the way vectors work. They're showing us how much and which direction. Okay, so what does that mean for a vector field? What is a vector field? Well, a vector field is a function in the xy plane up in the top left corner here. Okay, it's just a function. What do we plug into a vector field function? Well, we plug in locations. So by location, I mean the x and y coordinates for each spot on the graph. So you're plugging in the spot on the graph, you're plugging in the location. So that's what goes in. So what comes out then? What comes out is a vector. Okay, so we put in numbers, and out what comes out basically, what's a vector? It's an arrow, right? So we're going to plug some numbers into some equations, and we're going to get an answer, and each of our answers is an arrow. Okay, so let me write that right there. A vector is just an arrow. Okay, and so I have an example here for you right over here. Here's our function. We have x and y going in, right? Because we have a two-dimensional plane. This is a regular xy graph, and so every spot on this graph has an x and it has a y, and so that's what goes into our function. You pick a spot on the graph, you get the x from that spot, you get the y from that spot, and then that's what we're plugging into the function, which is in these brackets over here. Okay, so these are just locations. Locations. And what comes out of this in these brackets, these are arrows. These are our arrows. They're going to tell us which way our arrows point and how much. the first number is going to be how far does it point left or right. The second number is going to be how far does it point up or down. Okay, and so I didn't want to take the time and make this really boring by making you plug in all these things here. I went ahead really nicely. I have all of these locations right here that I plugged in, and then in each bracket is the answer for each one of those locations. So for the top one, we're doing x minus y. Here's x, here's y. 1 minus 2, that's negative 1. 1 minus 3, that's negative 2. And so you see every single one of these top numbers. How do you get that one? You just do the first number minus the second number, and it'll work. Okay, I did all the work for you. Okay, so now all we're going to do is go to each one of these spots and put an arrow that points in these directions. So the first thing I'm going to go is go to spot 1, 2. So here's spot 1, 2 right here. And from there, I'm going to draw an arrow that this is negative. So it's going to go left 1, and then it's going to go up 1. So kind of like that. Now I go to my next spot, which is 1, 3. Here's my next spot, 1, 3. This one is going to go left 2 and up 2. Kind of like that. Then I go to my next spot, 2, 1. So 2, 1, that's right here. This one's going to go to the right 1 and down 1. Kind of like that. 2, 3. So 2 now up 3. This one's going to go left 1, up 1. Kind of like that. Okay, 1, negative 2. So 1, now we're going down. This is my spot, 1, negative 2. And this one's going to go to the right 3, down 3. 1, negative 3, so we're down 1 more here. To the right 4, down 4. And so that's going to look like that. Then the last two here, negative 1 and 1, so that's right here. The arrow is going to go left 2, up 2. Literally every single one of these arrows is coming from these here on the right. I'm going straight down in order, and then I'm on the last one, negative 2, negative 1, 2. So that spot's right there, and that arrow is going to go left 3, up 3. So like that. Okay, and so you can see here is that what do we got? We've got a bunch of arrows on our graph, right? How do we know how big each arrow is and which ways it go? Well, that comes from these over here. And where did those numbers come from? Well, we plugged in the location. So at 1, 2, you take 1 and 2 and you plug them into this function, and the arrow has to go left 1 and up 1. Okay, and so this is what a vector field is. It's just a bunch of arrows. It's a function, and we can graph that function. What goes into the function is the location, your x and y numbers from each spot on the graph, and what comes out is these arrows. Okay, every spot on this graph would have an arrow, every single spot. Okay, so I'm obviously not going to go ahead and do all of those. There's some pretty advanced computer programs. They're kind of expensive and probably not something that you need, but we have the technology that can do that stuff for us if we needed to. Okay, so that's what a vector field is. It's just space, and that space has arrows in it, and the size and direction of those arrows depend on where in space you are. So how does that relate to physics? Well, why, like right here, why do we care about this? Well, let's think about gravity. We learned last time that any two objects with mass will exert a gravitational force on each other. So you and the computer sitting in front of you have gravity between you. The computer is pulling you towards it, you're pulling the computer towards you. But remember that the only reason we don't notice these things is because those forces are really, 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 really small, especially compared to like gravity from Earth. Or the computer is pulling you towards it, but friction keeps you from actually going at the computer. And like I said, the forces are really small. So anyway, the example that we're going to focus on right here is we're going to drop a water balloon off the bleachers, right? And gravity, according to what we talked about last time, the Earth exerts a gravitational force on the balloon, right? The Earth pulls the balloon down. And it was also talked about last time, that's not the only thing that happens. that the balloon exerts a gravitational force on the Earth. And this has to happen. This is Newton's third law. Remember back to our forces unit. Every force has to have an equal and opposite force. Okay, so we drop a water balloon off the bleachers, and the Earth exerts a gravity force on the balloon. The balloon exerts a gravity force on the Earth. And let's just draw ourselves just a little picture here. Not very complicated. There's the Earth. There's the water balloon. Okay, and it's falling towards the ground. Okay, so, but here's the thing that's weird. Isn't that's strange, right? That's weird. So the Earth is somehow able to exert a force on the water balloon without touching it. We know what it's exerting. It's gravity. What is it exerting? It's gravity. We know that. We've experienced gravity all of our lives. But how does it actually do that? Consider the fact that the Earth and the balloon is not touching it. So like when you're walking through the grocery store, you're pushing on the cart. You're making the cart move because you are directly touching the cart and pushing on it. So that's how you're able to make it move, is you are pushing on it directly with your hands. How does the Earth actually make the balloon move without touching it? So here's how that happens. What's really happening is first the Earth is going to alter the space around it, or the area around it, the air that you can touch and feel. The Earth is altering that space. It's changing what the space is like around it. What it does is it creates a gravitational field. There's that word field, which is why we were just talking about a vector field. Okay, so the Earth makes a it makes a gravitational field, and then the gravitational field is what actually exerts a force on the balloon, causing it to speed up towards the ground. So it's a little bit deeper than, just the Earth is pulling on the balloon. What's really happening is the Earth is making this gravitational field, and the field is what exerts a force on the balloon. Okay, so that's exactly what we're going to talk about right here, is the gravitational field. Last time we talked about mostly gravitational force. We're talking here today about the gravitational field. But we will start with the force. That's nice. We're going to start with something that you hopefully remember from last time, or kind of familiar with. We're going to start with the equation for gravitational force. Here it is. The gravitational force is equal to that big G, that super, super small constant. It's just a number. It's always the same number. And instead of writing that number, we just give it a letter. It's G. And then we have mass 1 times mass 2 divided by r squared. Remember, r squared is the distance between m1 and m2. So how far apart are these two things? That's what goes in r. And again, you take that fraction and multiply it by this number g to get f. It's always the same number. But let's say we're not interested in the force between those two objects. What are we interested in? What we are interested in is measuring the strength of the field that is generated by m1. So we're only concerned here with m1. I really don't care about what's going on with m2. I want to know, okay, so we know that m1 is going to make a gravitational field. Okay, m1 is going to make a gravitational field, and we want to measure how strong that field is. Okay, we want to measure what is m1 all by itself doing to the space around it. Okay, so that means we're trying to ignore m2. So how does that change the math? Well, it's really not that hard. You just take the same equation and you literally ignore m2. Okay, and there's your equation. See this equation? G times m over r squared. It's almost the same equation, except this one only has one m in it, right? We ignored m2, and so now we just have one m. Otherwise, the equation is exactly the same, just with one m instead of two. Okay, but how would we measure this? Okay, so this capital G with the arrow above it, that represents that's gravitational field. Capital F, that's force. Little g with an arrow on it, that is the gravitational field. Okay, so how would we actually measure this? Because we don't have a tool. Like you can get a stopwatch, right, to measure time. You can get a ruler to measure how far apart two things are. We do not have something that we can just go grab to measure a gravitational field. So how do we measure it? What we can measure is gravitational force. We know how to measure weight, right? We all have a scale. When we have stuff that we can use to measure the weight of something. Okay, so, and remember, that weight, that's a force. So I'm going to start with that over here. We're trying to measure the gravitational field We can't measure that directly. We don't have something to just get that force, but something that we can measure is the force, their weight. We can measure their weight. Okay. So then, well, what do we do with that? We can't measure the field, but we can measure the weight force. So what we do is we pick an object to test, and here we're just going to call that it's got mass, and so its mass is m test. Okay. Remember that the g field is the same as the force, but without m test. Okay. So mathematically, how do we remove m2? Like, look at this equation. We just got rid of m2. How would we get rid of m2 mathematically? We would have to divide it out. And so here we have the force, which we can measure. But what did we do with the force? We ignored m2. We divided it, which means we divided it out. So that's exactly what we're gonna do here. We're gonna take the force and we're divide it out. Okay, so what you see here is that this is another way. This is how we would actually measure gravitational field if we wanted to. And this equation over here is a theoretical equation. Okay, so this they both work. This one's just theoretical, but this one is how we would actually measure this g if we wanted to measure it in real life. But still, both completely valid equations. That means that as far as if you're trying to calculate this just from a problem with a calculator, you have two equations to pick from. You can use this one or you can use this one. It just depends on what they give you. Do they give you the mass and how far apart the thing and how far away you are, or do they give you a force? And so that's the kind of thing that you got to pay attention to. That will tell you which one of these two equations you need to use. All right, I actually don't have a whole lot left here. This is the last slide right here. So we're going to finish up this discussion about the gravitational field. I put the equation right up here. The gravitational field is equal to the weight divided by the test mass. Okay, so let's take this equation, and what we're going to do is we're going to solve it for F, and that's going to look like this right here. F equals mg. Okay, F equals mg. And that all I do is take this g field equation and solve it for F. Well, let's also look at Newton's second law, because these look pretty close, right? Newton's second law says that the total force, that's what net means, is the total force, is equal to ma, mass times acceleration. Okay, these equations look very similar, and so we can make a conclusion here that G and A are the same if the only force is gravity. A, the acceleration of an object, so A will be the same as G. Your acceleration will be the same number as the gravitational field number if gravity is the only force. If gravity is the only force. Okay, so not something that's terribly too complicated, but it is kind of important, because if you think about it, when you drop something like the balloon off the bleachers, how fast does it speed up? It speeds up at 9.8, right? We use that number 9.8 a whole bunch of times for things that were just falling through the air. That 9.8, that is how fast it's speeding up. And 9.8 is how fast it's speeding up, which means that it is the acceleration. But because when you drop something off of the bleachers, the only thing that is pushing or pulling on that balloon is the earth pulling it down. And so because that's the only force, the A is equal to what G is, which is 9.8. G is 9.8. And because when you drop something off the bleachers, gravity is the only force. So that means A is 9.8. G is definitely 9.8. And because gravity is the only thing, A is 9.8 when you drop something off the bleachers. Okay, so moving on, we're almost done here. What does a gravitational field look like? Okay, for something that's mostly spherical, right? The Earth is round. It's not perfectly right, a smooth, perfect ball, but it is roughly a circle. It's a sphere, not perfect, but it is, right? So what does a gravitational field look like? Remember, a gravitational field is a vector field. So what am I going to be doing here? I'm going to be drawing a bunch of arrows. Which way does the gravitational field always point? They talked about it last time. Gravity is always attractive. So no matter what, whatever is around the Earth, those two things will always pull together. So that means that it should be pointing at the Earth. Oops. All right. Yeah, it should be pointing at the Earth. Kind of like this. No matter where I'm at, they should always point at the Earth. I'm not going to go all the way around just because it is taking a while. Okay. And something that's important, right? And it's something that makes perfect sense is that the farther away you get from Earth, the less gravity you feel. So right behind this arrow is another arrow, but this one cooperating with me here. But this arrow would be a little bit smaller. And then behind that arrow would actually be yet another arrow, but even smaller. All right, I think we get the idea here, right? So it's always going to point in at all gravitational fields will always point at the object that is making that field, and the farther you get away, the weaker the field is, and so that means you get a smaller arrow, right? And this really is a vector field, right? What do we have? We have a bunch of arrows in space, and which way do those arrows point, and how big are those arrows? Well, it depends on where you are, right? Over here, it's going to point to the left because that's towards the Earth. Over here, it's going to point to the right because that's towards the Earth. And as far as how big the arrow is, well, that depends on how close you are. The closer you are to the Earth, the bigger the arrow is. You'll feel more gravity. Okay, and so this would go all the way around, and really this whole area should be completely full of arrows that all point towards the center and get smaller the farther you get out. Okay, so this is not the only thing that works like this. We're not going to get too deep into it, but there is a lot of similarity between gravity and electricity. What else works this way is static electricity, right? We did a bunch of problems like this in our first semester in the very beginning of the year, where we've got two charges and you want to look at, okay, well, how much force is between them, right? If they're the same sign, then they're going to push apart. If one's positive and one is negative, they're opposite. They'll pull in towards each other. They'll attract. So these right here, of course, these would push out. And we had this equation. And I had a question like this on our last assignment that asked you to look at the gravity equation and find me an equation that is very similar to it. And here it is. This was our equation from static electricity. Looks very similar to gravity, except instead of a capital G, we have K. Instead of masses, we have our Q's. And so this works exactly the same way as gravity. If these are both positive, so they would push apart, right? But how does Q1 actually push Q2 away without touching it? Because it's not. What's going to happen is Q1 is going to make a field. This time it's not gravity, it's electric. Q1 will make an electric field, and then that field is what exerts a force on Q2. And so just like with gravity, we can measure the field made by this electric charge. And what do? We just ignore the other thing. Here's Q1 and Q2. I don't care about Q1. I just want to know what Q1 is doing to the space around it. And you would have this equation right here. See what it does? It just ignores Q2. Okay, so if we want to know how strong is the field that's being made by Q1, well, then you just ignore Q2. And there's only Q1 in this equation. Okay, so a lot of similar. The bottom line is AP is just going to want you to recognize probably how similar gravity and electrostatics are, and they are pretty similar. And so that's something that as you get closer to the AP test, you want to be studying, looking for ways that electricity and gravity are similar. All right, we are finished. You want to make sure that you complete the assignment that's on Google Classroom. Have a good one, everybody. See you next time. Maybe. I don't know. We'll see if you like this, we'll do it again. I don't know. But anyway, ta-ta for now.